All right, welcome back for day 20 of Advent of Code. I should bring my microphone down. There we go. So, where did we pick off? Monster Messages was yesterday. That was that gigantic. Oh yeah, this was fun. Cool. And now, oh yeah, please do not disturb. There you go. Cool. So now we're about to start on the next part of our adventure, which is in this tab. Day 20. Here we go. Jurassic Jigsaw. Oh, what is it? It's Sunday today. Okay. The high-speed train leaves the forest and quickly carries you south. You can even see a desert in the distance. I prefer seeing a desert in the distance, honestly. Since you have some spare time, you might as well see if there was anything interesting in the image the Mythical Information Bureau satellite captured. Okay. After decoding the satellite messages, you discover that the data actually contains many small images created by the satellite's camera array. The camera array consists of many cameras. Rather than produce a single square image, they produce many smaller square image tiles that need to be reassembled back into a single image. Each camera in the camera array returns a single monochrome image tile with a random unique ID number. The tiles, your puzzle input, arrive in a random order. Oh, great. A random ID number, okay. And the tiles arrive in a random order. Well, that's fun. Worse yet, the camera... Worse yet, but wait, there's more. The camera array appears to be malfunctioning. Each image tile has been rotated and flipped to a random orientation. Your first task is to reassemble the original image by orienting the tiles so they fit together. Okay, to show you how the tiles could be reassembled, each tile's image data includes a border that should line up exactly with its adjacent tiles. All tiles have this border, and the border lines up exactly when the tiles are both oriented correctly. Tiles at the edge of the image also have this border, but the outermost edges won't line up with any other tiles. Oh man, okay. Woo. For example, suppose you have the following 9 tiles. Well, hot damn. All right. And the tiles are how big by how big? I guess we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 by 1, 2, 3, 4, 5, 10 by 10. So they're 10 by 10. Okay. By rotating, flipping, and rotating and flipping. Jesus. Okay. You can find a square arrangement that causes all the adjacent borders to line up. For reference, the IDs of the above tiles are that. Check that you've assembled your tiles and multiplied the corners. Okay, the IDs of the corners. Well, hot damn. How are we gonna do this? Okay. So, just thinking about ways we can represent these tiles. So, let's copy this. Okay. Yeah. No. Come on. There you go. So we're day 20. New folder. Day 20. So maybe let's think about an individual tile, and we will think about what that means in terms of how we can approach the problem. It's kind of maybe it's kind of backwards to think about it that way. I guess we're not gonna do. This is gonna be our input. So let's just do input. And then we'll just look at an individual tile. And okay, so we've got these tiles. Let's just grab these down below so we can take a look at them. So they've all got IDs, and that's fine. And they've got these, I mean, the one property that we really care about is what the side looks like, right? So we've got these tiles. So let's start with a single tile and just talk about a single tile first. Then we can talk about the tiles together, together after that. Okay, so we got the single tile. Now, it's got a side, and a side is either on or off. It has 10 bits that are on or off. So we could express this side as a number if we parse this into like 1 0 0 0 1 1 0 1 0 0. So what is this? This is a binary number. This will be unique. And then what is that? Parse int binary number base 2. Let's pull in log. I don't know why Siri keeps activating my iPad, but that's fine. So let's grab log, let's console, and let's log that. Let's see what it gives us. 564. So this gives us effectively a number. If we do the same thing with that, so the right hand side, this would give us 0 and then 1. So we could also get a number for effectively what the right hand side would be by converting those into, whoops, come back. Converting those into, oh, doesn't like that. Here, because it starts with a 0, that's why. So by converting those into a binary number as well, we can get a number. We can get a number for all 4 sides this way, right? We can turn these into numbers, and then we have an easy way to compare them. So that's what I'm thinking is, what is this? 564, 318. Okay. So effectively this thing would become, 564 by 318 by whatever the bottom number is by whatever the right side is, right? That's sort of like the idea that I'm kind of going for, is that we would create a tile, and the tile would have these properties. If we rotate or flip these, so effectively what we can do is we would just be rotating or flipping these numbers. Like we don't even care what the tile looks like. We just want to generate these 4 numbers, I think. And it would have an ID, like ID 1 2 3. And so let's say this tile had the following properties. Okay, so that's kind of annoying. Okay, let's just pretend that this was a 564 by 256 by 318 by 684 or something like that. Let's say that's what this box looked like, right? So this is our box. So what we could do is and that would be expressed as an array of, let's say, the four cardinal points, or not cardinal points, but the 4 values. Cool. So that's our definition of the box. So it'd be ID is this. This becomes our definition. So now if we wanted to rotate this, what we would do is we would just grab one of those, stick it over there, and bam, we've got a rotated box where we've taken the box and we've rotated it. We could also flip the box on either axis. So we could do, we could put that there and then that there. We could flip the box on the other axis as well, where instead of transposing the second and fourth values, we transpose the first and third values, and that's all a flip is. And what do we end up with? We basically end up with how many, so we can flip it, we can rotate it, and how many combinations of that can we have? It won't be just any combination of the numbers, because if you have two adjacent sides, they must remain adjacent. They must always be adjacent. Even if you flip it and then rotate it, they would be adjacent, just in the opposite order. So that cuts down on the number of permutations that we have. And then ultimately, that's like, that'll be part one. It'll give us a set of what this box can look like. And then we'll do that for all the boxes. And then what we want to do then is we want to go through, I guess, trial and error, and be like, we need to find the box's position by trying to maximize the number of other connections that it can make. So, and what does that mean? That means that this box here is going to find like a neighbor. Here, let's grab these. Oops. Trying to, like, drawing in a text editor is like a skill I have yet to master. Okay, so we got that. There we go. So it's gonna have a mate with a 318 here, and then, you know, other numbers here, you know. So this is the important thing, is that it finds its mate, and it may have to find several mates. And the interesting thing about finding these mates, I think, will be that when you're done sort of like processing all your boxes, you're gonna probably find a value in one box that doesn't exist anywhere else, and that indicates that it should be an edge piece. So maybe that's a hint on how to do this faster, right? Like, so over here, like this number, whatever this number is, this doesn't need to appear anywhere else. So we can know that if this number doesn't appear anywhere else, that it can't touch any other boxes. So this has got to be an edge piece. And then similarly, this would be an edge piece, and this would be an edge piece. And we could go further to say that we know that this box must be an inside box, because it has no edge pieces. This box must be, you know, like a left or a right edge, or a top or a bottom edge, because it has one edge piece. And then these must be the corner pieces. We could, and really, I guess all we care about is we only care about what the IDs of the corner pieces is. So if we go through and we identify all 4 corner pieces and say, hey, these are the corner pieces with 2 unique numbers that just don't end up anywhere else, we don't actually care about what the whole thing looks like. All we want to do is find the corners. Okay, so let's do that. That's interesting. So let's find these corner pieces. So I'm going to delete all these, and let's jump into it. It's always good, I think, to sort of like talk through what you're thinking about, because this is how I discover that I might not have to do a lot of work, because it's a pretty daunting task to be like, oh, turn all those things into this picture. Maybe we don't care about the picture. And we don't. All we care about is the corner tiles, and we can identify the corner tiles because they won't match up with anything else. And also, we might not even care about the rotations. Okay, so maybe we will care about the rotations, because maybe there will be it's possible that this number and this number will be identical. And if that's the case, then we wouldn't be able to prove that they're corner pieces. We would have to determine that they could be corner pieces. Anyway, let's hope we get lucky and don't have to worry about that. So we got defs, we got what is it, tests, and then we got run. Okay, so these are, I always capitalize the U. Okay, so we got our things. Tests, we're going to be asserting that given this input up here, so we're gonna have to parse these tiles, and we want to say that the 4 corner tiles are these IDs. Okay, so parse tiles input, or this is going to be parse input. And what do we want back from parse input? We want let's get an object, because that way we can have the ID of the tile and then the coordinates, or the sides, I don't know, the side IDs. So this is kind of what we want. We want something like this, and then that followed by, oops, that. Okay, cool. So I guess we should do something like that. We're just, I mean, this is just, it's not, it doesn't need to be code. We're just drawing it out. So that's what we want. So let's bring in our old friends log, which I had earlier but deleted for no good reason, and assert require assert. Cool. And so we're going to define parse input. This should be indented 4 because it's literally a coffee script. And then this is the output we want, and this is the shape of the data coming in. It's a series of equals wall of text, and okay, so, and this is what we're going for. Okay, and we're getting multiple of these. Okay, so and then all we want to do, so we want to parse, let's first split them across. Split them into tiles. So tiles, I guess text dot split split sploit splot split. There we go. So we're going to look for all the tiles that are separated by 2 returns, and then we're going to map them into individual tiles. Oops. So this is going to be more text. And individual tiles, there's going to be a header row, and then there's going to be data rows. So we can say text dot split. I guess this is overriding text. Maybe we should have tile text. Tile text. It's probably fine, but whatever. Text split. Oops. Gotta be these dudes for new line. So we're splitting on new line. In fact, we're gonna say header, comma, I don't know. Call rows equals that. So we're gonna do that, and let's grab the ID. So the ID is going to be just the four digits. So ID is going to be what is it? Header. We want to match that plus dot match, and this is going to be the whole match, the ID. Actually, I think we can just do, can we just do ID match like that? Let's try it. Okay, let's got the string, and we'll do that. Whoops, log. Ooh, it's not a function. What? Does it have to have? No, match is not a function. Exec. I guess exec, yeah, exec will give it to us. Why is, oh, it's match on the string, match. There you go. And if we don't use a capturing group, I think it'll just give us, yeah, it'll give it, the first one will be the thing that matched, which is fine. Okay, so we'll do that. And then we got ID, and then we don't care about the rest. And in fact, I think we can actually just do that. And then this is going to be header.match. Okay. Cool. So that should work. And then what do we want to do? We want to return from this map. We want to do ID, and then we want to do the 4 numbers. And we'll call those edges, because why not? Okay. So this is what we want to return. We've got the ID. Now what we need to do is we need to figure out what the rows are, or the edges are. So I guess what we can do is we can say, so we want to figure out the top and the bottom. So that's going to be the first row and the last row. And we're going to want to map those to a binary number. So what we're going to do is we are going to grab the first row, so rows 0 dot place, that with a 1. I wonder if we actually do we even need, we don't need to make numbers out of this. I was just thinking the numbers might be convenient, but I mean, just the string itself would probably be fine. But let's make numbers. So let's figure out how to turn a row. Let's log. This is going to be an array. I guess what we can do is we can say that. Oh, it's actually going to be like a string, right? Okay, and then we're going to want to replace. Okay, no, so it only replaces it once. Replace all. No, it's worth a try. So let's do a global replace on that. Cool, and then we're going to want to do a global replace on the results with dot, but a literal dot with a 0. Okay, so that gives us a number. Okay, replace that. And then what we're gonna do is we're gonna parse int that in base 2. So that's gonna be, this is gonna be the top. Okay. Then we're gonna need the bottom, which is exactly the same as the top, except instead of rows, it's gonna be rows at rows dot length -1, so the last one. Then we're gonna need the right. So how do we do the right? The right is gonna be, I guess, rows. So what we're gonna wanna do is we're gonna do like rows, and we're gonna map them. And we want, for each row, we want the row, the last one in the row. And then we're going to join that into a string. Okay. So that'll give us the last one, and then we're going to call the stuff on it. So replace. Okay, and then we're gonna want to throw all of this into parsin, and this is gonna be 2, like that. So that's gonna give us the right. So let's see if that even works. And get out of there. You know what? Let's just stay consistent for readability. All right. There we go. Let's see if we can make that work. So let's just test this down here. So we're gonna do parseInt log. It's like a scratch pad. Log. Is it lol equals? No, it doesn't like that either. Unexpected indentation. Oh, it's because it's indented by 1. There you go. There you go. So let's log that. Yeah, 702. Okay, and then let's try it. I mean, this should work as well. Rows, rows, map, and then join. Okay, so that's the right. So this is top, right, and then bottom. We'll just copy this bottom over here as well. I would actually love it if I could call it like this. Can I do that? No, I can't. Okay, it'd just be a little bit more readable. Yeah. Okay, top, bottom. So this is going to be rows, and this was just rows dot length -1. I really wish there was array last in JavaScript. Maybe there is array JavaScript. They add new things all the time last. I mean, we could do pop, but that destroys the array, or it modifies the array. Yeah, like why isn't there an array dot last? I don't know. Anyway, be so convenient. So that's bottom, and so that's right is the right, and then we want left. Left, and this is going to be row 0. This is going to give us all the lefts, and then edges is going to be. I mean, we could just do top equals. Yeah, may as well. And we don't need the comments. That's my my little trick is if you can name variables right, then you don't need comments, because the variables themselves are kind of the comments, like in this case left equals that. And then our edges become top, right, bottom, left. Cool. Let's put some spaces in there, and that's what we return. So this is one way we could do it, which is ID and then the thing. The other way we could do it is as an object. Like, you know what? I think that's what we sort of decided on at first. So let's do that instead. And then each one will say ret of ID equals like that, and then we can return ret. So let's parse. Let's parse input and see it blow up, and then we'll know how to fix it. So log parse input. It didn't blow up. Okay, that's interesting. Maybe we should just give we should turn these into integers as well, the IDs, because we're going to be multiplying them later, and that might be nice. So where's the ID? I mean, what we could also do is we could start assigning the object here. We could say tile equals could say tile equals ret parse float ID. So we could do that, and then we could just say, and that is equal to an empty array. And then we could say tile dot push, and then that would be the top. And then we could just, we don't even need to return the tile, we just need to return tiles. So let's turn ret into tiles. Okay, tiles, and then this can be tiles. Okay, tile push. So that's, at this point, we should probably put our comments back top. And then this is going to be right, bottom, tile dot push. And then left, oops, tile dot push. Okay, and then we don't need that anymore. And then we're going to return tiles at the end. So what do we got? Tiles, but we're still, oh, it's always going to stringify the keys. I don't know why we bothered with that. That's super annoying. Okay, cool. Well, whatever. Okay, so now what we want to do is we want to find, we've got each one of these tiles right now is an object, or is an array. And while we could, what we want to do is we want to mark the number of unique values, right? We want to find which sides are unique globally. So what we want to do there is we need a list of all the sides. And we need to find out how many of the sides per tile occur only once in that. Okay, so we've got tiles. So what we want to find is we want to find corner pieces. And this is going to take in tiles, which is an object. Okay, so the corner pieces, so we only want the corner pieces. And this is just going to give us back the guaranteed corner pieces. And I'm hoping that that'll be good enough. So let's find out. So it's going to give us back tiles. So what we want is we want to map the tiles and just get their values, right? So each tile is an array, and we want a list of all of the values. So let's do that. Dot values tiles for tile in. I guess what we can do is we can just say for ID tile in tiles. So let's get all sides, and then let's sides equals sides and tile. So we're just gonna merge them, and then what we should have is we should have a full list. Let's log sides at this point, or I guess we could just return sides. Okay, this is going to be like log corner pieces parse input. This is only giving us a single value. Okay, so this is giving us nothing. So sides equals that. So sides equals for ID tile in tiles. Oh, of tiles. There you go. So this is all the tiles. So we found a 24, and there's no other 24s. 966. So 85, 89, 18. So there's a lot of uniques in here. Are they? God, I hope they're not all unique. Oh, you know what? When you rotate. So something we didn't consider is when you rotate, sometimes these go in sometimes these go in one way and sometimes they get reversed, right? So if we rotate this down to the bottom, then it's the other way. And similarly, this is going to be more complicated than we thought, because the numbers change based on the rotation. So how is that going to affect how we want to find the corner pieces? So if we rotate this 180 degrees, this side is still going to exist, but it's going to be backwards. So it would give us a different binary number. And I mean, there may still be a case where if we calculate all the possible sides, so we need to flip. So flipping doesn't matter for this, but rotating does. So each of these binary numbers that we put in, we'll need to know the forward and the backwards numbers. So that would mean that, okay, so each one of these, we can try it and try to be naive with just any possible number and look for the ones that are guaranteed unique. Oh, see, but this is going to produce a lot of unique numbers possibly that don't matter because they won't be in the final. Maybe we will need to start pairing them off. Ugh. I really don't want to have to assemble these as tiles. Okay, by rotating, flipping, and rearranging, you can find a square arrangement. Let's see if maybe they give us some subtle clues in the text itself. Okay, so after decoding the satellite message, you discover that the data actually contains, zoom now. Random unique ID number. The tiles your puzzle input arrive in random order. Camera array appears to be malfunctioning. Each image has been rotated and flipped to a random orientation by orienting the tiles so they fit together. Okay. So if we rotate and flip this tile randomly, what it might produce is it might produce a piece that has more or less than two distinct edges, two distinct values. We're only interested in a piece that has exactly two distinct edges. So maybe that's our saving grace. Maybe that's what we can look for instead, is a piece that has exactly two, and maybe the pieces that have exactly two, we're gonna have to permute all the different flips and rotations. So this flip and then the left and the right will be the same. And then if we rotate, that's the same thing as having, the numbers would be the same. So we're gonna have 8 numbers per tile. We're gonna have forward and backwards for each side. But we're gonna have them in different combinations. So what is that going to look like? That's going to look like we're going to have forwards, 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 forwards like this. And then if we rotate that, YouTube is angry with me. Bitrate is low. Okay, sorry, YouTube. So if we rotate this once, this forward is still going to be forward. This forward is going to be backwards. So let's do left, top, right, bottom, just nomenclature. So if we rotate this, the top is going to go here. It's still going to be forward. The right is going to go here, but be backwards. So we'll do a lowercase right. Then the bottom is going to go here. So bottom is going to still be fine. And then the bottom is going to go to the top and be backwards. So left rather. Okay, so we're going to have that. Then when we do it again, the left is going to go here. So when we go from the top to the right, we maintain the order. So, okay, left and then left. So when we go from a vertical to a side, we maintain the order. It's when we go from the side that we flip the order. So we need to reverse in those cases. Okay, so so left goes to, let's continue doing this. The left goes to right. This used to be a top and it stays a top, but it flips. And then this was right, but it goes to here and it stays. And then this used to be bottom and it goes to the top. So right, we've got the top and the bottom, and right and left have flipped, and they have flipped. Okay, and then we need to go back around again. So it's only going to be there's going to be 4 things. So this bottom goes to here, and no, this stays, and then bottom, this, what was this, a left, it goes to here and it flips, and then a right goes to, what was that? That was a top before, so it goes from top, right, and then top, this was a right and it goes to here, but it flips. And then finally, whoops, right goes to here and it stays the same, bottom goes to here and it flips, and then we're back in our first position. So these, this is the progression. Is it goes from that. Okay. And how can we express this as how can we express this as a function, I guess, is the question. I'm gonna copy this over just so we can have like a visual just a visual key to help us. Okay. Ooh, okay. So we're gonna need a new function here called permute. And before we lose it out of our paste buffer, let's just put it in here, make a block comment. So this permutes the tiles. Okay, so, and really what we want is we want 4 strings, I guess. That would probably be easiest. Because otherwise we need to figure out what the inverse, I guess what we could do is we could have the inverse. We could just have a function that inverses a number into its reversed binary counterpart, because that's really all we care about. Rather than flipping the string. Well, I don't know. We've already got the strings. Well, at this point, we've got a tile. We need a version of this tile. And there's 4 states for a tile. And each of those states has 4 numbers. So we need to figure out what the state of the tile is. So for each one of those states, we need to figure out what the state of the tile is. And we need to know that in that state, there's exactly 2. So maybe what we can do is actually we can build this into a tile object. We can just have a, yeah, let's do that. Class tile. Tiles are getting more complicated. Constructor, and it would be helpful, I think, for me to be able to just call like rotate or flip or whatever, or permutations or something on the tile itself. That also allows us to give the tile so an ID and rows, and the rows will be an array of just rows, so it'll be literally ID and then rows here. So we'll just create a new tile, and then we can have methods to figure out all these numbers. Okay, so or I guess we could take in tile text and we could just do this stuff ourselves. Let's do that. So get header and rows equals tile text split. Okay, and then ID of that tile would become right. Oops, there we go. Okay, so that'll give us a set of tiles. So it'll be map tile, oops, tile text, and we could say tile equals new tile and tile text. So this will give us a new tile. And then what we can do is we can figure out right and left, top, right, bottom, left. So we need to figure out the states. So we're going to have states for the tile. And the states for the tile are going to be every permutation of these guys. So there's top, left, bottom, right. Left, top, right, bottom, but where left and right are reversed. Same with bottom, left, top, right, where they're all reversed. Okay, so we're gonna need these four states. And we could, so what could we do? We could calculate what the 4 state strings are and then calculate what the numbers are. So we could do top. Okay, so we could figure out a side. So we'll do top, and then we'll say forward equals true. And that would be this guy. Or I guess we could say reverse equals false by default. And then what we could do is we could ret equals, and then we could say ret equals, can we reverse a string in JavaScript? Is there string reverse? Or do we have to do it with an array? String reverse. 3 ways to reverse a string in JavaScript. Number 2 will shock you. Okay, so with a built-in function, split, reverse, join. Split string reverse. So split, reverse, join. Yeah, we could do that. Reverse a string with decrementing for loop and with recursion. I'm okay with strip reverse join. Strip reverse join. Here we go. Okay. Equals ret dot split reverse join if rev and then ret. Oops. So that's what we got. And then what we want to do is we want to parse int ret base 2. Okay, so that's top, reverse false. So let's do the same thing. That'll also be bottom. And really we're doing a lot of the same work in a lot of these cases, except it's just about the array of rows that we bring into these. So let's pull this stuff into, it's like, say bin to deck equals, and this, what are we always giving it? We're always giving it a string. And then this will just be this can be I guess our symbols to decimal. So this can be our fingerprint function, and our fingerprint function will do rows be, whoops, come on, there you go, string place replace, and then what we can do is we can say reverse equals false. We can do this here. If rev, and then we can parse in, oops, parse in ret2. Okay, so this becomes fingerprint rows O, and then we'll pass in rev. Cool, and then bottom equals rows -1 dot length. Actually, you know what, we can actually I think we can do this in CoffeeScript. Let's check. I do like how CoffeeScript paves over some of this crap. So, and what do we want to do? We want to do rows -1. Let's alert that. Just to avoid having to open the console. No, let's open the console. All right. So what's rows -1? Rows is not defined. Oh, rows. Undefined. Yeah, rows equals. We do that? No. Oh, we do up to -1? 1, 2. No. It'd be nice if we could do this, but I don't think that works. Oh yeah, slice -1. Nice. So we can do that. Cool. Cool. So that's top and bottom, and then left and right. Right equals false, and what were left and right? Left and right, we were just gonna rows map rows left -1. So right. Oh yeah, and we want, this is gonna be rows. Woo, rows. Okay, so we're gonna fingerprint rows, map row, and row, we want the last one. We want the last one. And then we're gonna fingerprint that. In fact, what we can do is we can just call fingerprint. We'll call fingerprint with reverse first. Oops. And then we can just chain that on. So rev is always going to be first. Okay. Rev. And then now what we can do is we can say rev. No, we don't need to add a bunch of confusing parentheses. Okay, and then left is going to be the same thing, but row 0, like that. Okay, cool. So now the states that we want are these guys. Okay, so, and what does that mean? That's top, let's put these in order. Top, right, bottom, left. So we're going to have top, go left, bottom, bottom. It's probably the really top, right, bottom, left. So this is probably going to be like the really annoying way of doing this. There's probably a way that I could generate these, but I don't feel like it. So we're going to call those with false because they're not reversed. Then we're going to want to call them in a different order, but I guess the order doesn't really matter, but you know what, let's just, for the sake of it, we're going to take the left and put it up at the top, and so that's true, true, and we're going to do the same thing again down here where we go and the bottom comes up to the top, and that becomes true, true, and then we're going to do it again where the right comes up to the top and this becomes false, false, like that. And then the fifth state, if we followed this any further, would be the top comes up to the top and that goes false and that goes false again, and that's exactly what we had in the first case. So these are our states. Whew. Okay, I'm hoping this was worth something. Okay, so we've got our states, and let's before we go any further, let's just try to, okay, tile equals new tile text. Let's see if this should give us a bunch of tiles. In fact, this I guess, I mean, it's a constructor, so it doesn't really, maybe can we just call it, can we just map it through tile? Let's find out. Because that would be awesome. So let's see, parse input tiles. Oops. Oops. Log. No. So we do need to do the long form. Tile is not defined. Tile is not defined. On tile. Where are we saying tile? Come on. Tile text, tiles. Oh, permute. Tile cannot be invoked without new. Okay, so that's what I thought. We do need to actually map text and then new tile text. And then this is going to be, is this a string? There we go. We'll give ourselves a hint. Cool. And right, that would be an array of tiles that we're getting back. So I'm okay with that for now. Let's consider it an array of tiles for now. And we don't need this. We don't need permute anymore. So corner pieces, that's TBD. Let's log parse input tiles. So this gives us a lot of tiles. And a tile has rows. Right. Okay, cool. Cool. So a tile has rows. And now what are we going to do with these tiles? We're going to try and find the corner pieces. So we need to find out when there's exactly two. So really what we want is we want to know for the states. We want a complete list of all values. So all side values. And what we're gonna get that is gonna be states, and we're just going to, so we're gonna call states, and for each state we want, actually I guess what we should do is we should see what states is for tiles. So we've got tiles equals parse input tiles, or parse input. So tiles, let's just get the first one, dot states. Let's log that and see if it's what we want it to be. String replace is not a function. Okay, so these aren't even generating properly. So rev string, so string replace is not a function. What? Rows map. Oh, I guess I should join them. Okay. So I guess I just did need to do that after all. All right, this bottom is not a function. Bottom. String replace is not a function. Okay, 193, 210, so 210. Okay, so what did it do? It gave us, that gave us the first one. Okay, you know what we're gonna do then? We're just gonna do the long form, -1. And we'll do the same thing over here. Was that row length -1? Okay, cool. Yeah. Cool. All right, so that's where we were logging something in somewhere right here. Okay. Okay, so these are the states that we've got. So what we want to do is we want to find so 210, 210, 210, 210. So this doesn't seem to be working because this should be theoretically producing the reversed. So rev false, if rev left So it should be, okay, so the second one should start with, oh, because that's a 0, so that's not helping. Let's try the second tile. Let's see if that is giving us still 1, 1. So left should be flipped. So this should be the opposite of 1. So clearly this isn't true. So, okay. I have a feeling reverse is not doing what we think it should be doing, because I think in JavaScript, so let's log ret, because reverse, let's just log ret twice. Yeah, okay, so this is exactly what I thought. So reverse reverses the array in place. So I guess what we can do is we can just make a reverse string reverse, and I can just take a string, and what we'll do is we'll say string equals string dot split. Well, we'll do exactly what this is doing, right? Okay, so ret equals string split. What happens if we call split with no arguments? Okay, and then we'll return ret join, and we'll say ret reverse. And then we're not joining with anything. Well, let's see, string reverse. Let's see what this does for us. Let's just log string reverse Kieran. Kieran, no, that's not doing it. So why is string reverse not working? String reverse split join. Do we need to do that? Ah, okay. Maybe we can do. And it's just because we weren't doing it on those. So let's try that. Yeah, okay, that does work. We just need to back it up. Okay, the split. Reverse join. Okay, so there's 1, 1. No, it's still giving us the wrong fucking thing. Okay. Oh wait, no, we got a new value here. So that was going from that to that. That should be backwards, I think, and it's not. So maybe that's not working. 710 564, so 5 1. Yeah, why are these zeros and ones not flipping? So when top goes to the next position, it should stay the same, and then when it goes to the third position, it should flip. And that's correct. And then when it goes to the fourth position, it should stay the same. Yeah, that's, I mean, I think this is right. So let's start with the last one, the left. The left should flip immediately, and it does. It goes from not being reversed to being reversed. So let's log what these are. So, and then let's log that and then return it. Okay, so 710, when it gets flipped, Okay, so let's do that and then say if rev log rev or log ret, and then okay. Okay, so oh, you know what? Maybe sometimes we're getting, oh, it looks like sometimes we're getting an array instead of a string. So where's top? Rows, the first row, as far as I understand, the first row should be, oh, you know, it's these fucking joins right here. Okay, there we go. Nice. And then this gives us 710, 498, 841. So then 841 gets flipped to 587. 587 gets flipped back to 841. So this is what we're looking for. All right. JavaScript. Okay. It was the same stupid bug twice. And we don't care about that. We can just do this. Okay, cool. Nice. So that gives us our side fingerprint. And then we've got, so we're going to want all side or all states. We want to print out the numbers for every state. And what we really, I guess what we really want, we want to know all possible values globally. So we're going to want the unique values. So unique state values or unique side values. And this should give us an array of 8. Okay, so it should be for state in states. Let's make a new set. We can, what is it, set add? I wonder, can we set dot add state like that? Set add state and then set to array. Let's find out. Unique side values. Okay. Nope. Set to array is not a function. Can we just do that? No. Can we just return the set? Yeah, set add. I guess let's just set equals that and set push. Okay, and then for val in state, we can set push val unless val in set, then we can just return the set. No, it's not working as well. Oh, gotta call it. Okay, so these are our unique values. So 710 only appears once. So 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 values, which makes sense. I wonder if we could, I mean, we could just maybe create a new, maybe we could do a set, but then we have to convert back to an array. I don't know. Okay, there we go. We'll just do that. No, do that. Okay, set push val and less val and set. Cool, so this is gonna give us our unique side values. So what we want is we want globally unique side values. So all side values equals, and we're gonna take in tiles, and we're gonna say for tile in tiles, tile dot unique side values. So we're gonna basically do the exact same thing that we're doing here. Except, okay, this is going to be for tile in tiles. And we're going to say for sides in tile unique side values. And then we're going to push, I guess, val in, and and that's val and set, and then return set. So this is going to give us all globally side values, all side values. So let's log all side values tiles. And see what that gives us. So this is all the globally unique ones. And then I guess what we're going to want is we're going to want a function that looks through these states and gives us possible corner states. So corner states. Corner states, and this is going to take in a list. I guess we can take in a list of all tiles. This is going to be all tiles. I guess tiles is all tiles because this is just a single tile. And I guess all we care about is if any of these states has exactly 2 values that are unique. Has exactly 2 values that are unique. So this has already been collapsed. So that's super annoying. Yeah, is this just going to become, so however many inputs, however many tiles? I mean, we could, oh God. Maybe what we need to do is we need to flatten these by tile. Like we just need to map through, oh, these are the 8 possible sides for each tile. That's something that we could do. Okay, I'm gonna re-up my coffee. I'll be back. All right. And we're back. All right. Let's see now. Where were we? There we go. There we go. Okay. Okay, so what were we doing? We were trying to get... We're doing all this work just to try and figure out the corner pieces like a cheap way. And it feels like this shortcut is paying fewer and fewer dividends the further we get into it. I guess what we could do is we could be like, you know, like what would it take to actually just try to find an orientation where, like, to actually rebuild the tile pattern. I wonder if that would be just as difficult as what we're trying to do right now, because at least it would be reasonably foolproof. So what we'd have to do is we'd have to find, I guess what we'd have to do is we'd have to find, we could do this like Sudoku, where we just start with a tile and we try to find any other tile in the set who has a state where the left matches the right of the current tile, and then keep going. And then we could do that. We could try and find that, and then for each one of these we could try and, like, then we need to know the shape of the tiles. I guess the other question is, what does the input look like? Is it always going to be 3 by 3, or is it going to be fucking huge? So let's find out. The input is going to be fucking huge. Okay, so how many tiles do we have in the input? Oops. Tiles, find tile. So we got 144, so it's gonna be 12 by 12 grid. Don't save. It's gonna be 12 by 12 grid, and here we have a 3 by 3 grid. So it could get messy. I guess what we'd want to do is we'd want to try and find rows. But we want to find a row. I guess what we could do is we could kind of just go out where we find the next one and the next one, and if that goes to that. I mean we could. It might take a while. Doing the 3 by 3 might be okay because there's a limited number of permutations that we need to try, but doing a 12 by 12 might expand to be extremely difficult, especially when all we want is the corners. That's all we want. All we want is the corners. We don't even care about the order of the corners. We just, yeah. Okay. Let's stick with our current plan of just trying to find the corners the cheap way, and then if we run into more problems, we'll look into just rebuilding the entire tile set, because, you know, it's always possible that part 2 needs us to assemble the thing anyway. So okay, so I guess all side values would be, what we really want is we want all, let's just see if this works. If this works and we can get our corner pieces because we get lucky, then we're okay. So this is going to be all side values. So this is going to be tiles, and what we're going to want to do is we're going to want to return the corner states. So that's going to be other tiles. So we're going to want to get all side values for tiles that aren't this one. So other tiles equals tile for tile and tiles when t isn't me. Okay, and then we're gonna get all side values that. So vals equals that. So this is the list of side values in tiles that aren't this one. And then we want unique side values for this tile. And we want to see unique side values for this tile. And let's other tiles. There we go. So we got the other side values, and we got the side values for this tile. And let's find out how many of these overlap or don't overlap specifically. So what we could do is uniques equals okay, for val in unique side values, I guess for val is terrible. All side values other tiles. So this other vals. Well, when val, I guess we can just collect them. Val, or I guess we can just say val for val. When val not in other vals. And we can say num equals 0. We can say num plus equals 1. And then we can return num. So, but this is only going to give it to us for the current state. So what we want to do is we want, see, this is totally not what we want. What we want is, we don't care about the unique side values. So corner states. So for state in states, what we want to do is we'll count them for val in state when val out another val is num. And we actually want to say states dot filter, and filter in JavaScript is select. Okay. I guess what we want to know is we want to know if any of them are exactly 2. So we want to know possible corner state. Yeah, so for state and state, there you go. So we're just going to go through the states, and what we're going to do is if this number, if num is 2, we're going to turn true. So then, yeah, and otherwise we'll return false. Okay. So other tiles, and we can just pass that in like that. I don't care. We'll keep that. So possible corner state. So we'll find out if it's possibly a corner state. So for tile in tiles, we'll say tile dot possible corner state, and here's the list of other tiles, and we will log that and see. Maybe what we'll want to return instead of true is we'll want to return ID instead of false. Okay, so false, 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 false. So they're all saying false. Val, not in other vals. So I was expecting this to give us, I guess let's just return num. No, this is going to return, it's going to do it once per state. So num is 0. If num is 2, we want to return the ID. Okay, and we're logging all side values for tiles. So For tile in tiles, log tile possible corner state tile. So it's always giving us false. So for val, num plus equals 1 for val in state when val not in other vals. So this is the other vals, which is all side values. So let's log other vals to make sure that this is actually just a single dimensional array. It is, okay, 501, and it has different numbers of, or maybe it doesn't. Let's find out. Length 48, 44, 46, 44, 48. Yeah, because of the number of them sharing. Oh, that's interesting because there's 44, 44, 44, 44. So that's interesting. So other vowels can be as high as 48 for the middle piece. It'll be 46 for most pieces, and it should be 44 for the corner pieces. So it's funny that that's not working. So log other vowels dot length. So I'll bet this is a way to find out. So we want the one with the minimum the 4 with the minimum overlap in this case, which is 44, and there's 4 of those. Those are the maximum overlap because we've subtracted 4. There's one with 48. Maybe I'm thinking about this wrong. T for T in tiles when tile isn't this. So that changes, and other vowels equals all side values, other tiles, and all side values gives us a unique set of side values. I'll bet this is the answer, but how is this the answer? So what does this give us? Possible corner state. What we could do is we could say this is like the inverse of the cardinality. So it's sort of like how many unique values there are in the rest of the board. And there should be, so how many junctions are there? So there would be 1, 2 times 3. So look at, I guess what I'm thinking is like, let's look at this. There's be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There'd be 12 junctions. There should be 12 junctions of overlap where the number appears twice, right? 3, 3, 3, 3. So 3 plus 3 plus 3 plus 3. So there should be exactly 12 duplicates. I guess that would be a way of finding the right inputs, would be finding the number of duplicates. So we want exactly 12 duplicates. And then so that's another way we could do it. We could run all the tiles through, and for every state of the tile, we could calculate the number of duplicates. And at most, the number of duplicates would change. Yeah, but that's going to be just a huge number of permutations. I mean, we could probably speed it up by saying like, no, it's just, I think it's a bad idea. Okay, so possible corner states. So, I mean, so return ID. So this is just giving us, for state and states, for val in state. Okay, so for val in state, let's break this out. On the state, if val not in other vals, the number is plus equals to 1. So this should give us this, the same crap, which is 46, 44, 44, 48, 46, 46. And let's log num. 0, 1, 2. And we're not, why are we not logging num? Oh my god, I will cut someone. Okay, cool. Okay, so again, num less equals 1. I always forget to call fucking states. Okay. So we can just say when val on other vals, and we can say num plus equals 1. Okay, and then we don't need to log this num anymore. Okay, so what else are we logging? We're logging other vals.length. Okay, so false ID, ID, false, false, false ID, ID. So this is giving us, god damn it. So 4 corners, it's giving us 4 corners. And I mean, we could multiply them together. I mean, so this is giving us, okay, where are we? Possible corner state. We wanna filter by this. So you could say tiles.filter, and we can say, okay, so this is the corner pieces thing. Is we want to say tiles. We want to say tiles.filter. Okay, T and say T dot, what is it? Possible corner state. And then all tiles. Okay, so corner pieces. So corner pieces tiles. So let's find that out. And let's log. Whoops. Let's log that. So that's giving us 4 tiles. Okay, so we're gonna filter, then map, and that's gonna be t.id, so it should give us 4 IDs, dot map, parse float, wow, there you go, parse float. Okay, so that gives us these, and we can multiply those. We had array multiply somewhere, didn't we? We had array sum. Oh, it was sum array. Mult array. There we go. Let's just grab this. Mult array. So then we can mult array corner pieces. Log, oops, multi-array corner pieces tiles. Let's see what that gives us. That gives us this number. Is that what we're looking for? No, it's probably not. Oh, 28. Yeah, it is. Okay, so this is what we're looking for. So we can assert that. I mean, we can try it. Assert is okay. So and then tiles is just parse input. So that's true, and I guess what we can do is we can just try logging acquire input. We can just try that and see if it gives us an answer. I mean, maybe it will, and we can move on. Input dot coffee. Save. Okay. Yeah, do it. Okay, and this is module.exports equals. Oops. All right, let's try it. So it gives us this number. Let's put it in, see if we get it. Answer. It's the right answer. Okay, so we got exactly 4 corner pieces, which is nice. So continue to part 2. Well, shit. Now you're ready to check the image for sea monsters. The borders of each tile. So, okay, well, before we move on, let's just talk about why this isn't a great solution. It's not a great solution because it predisposes, or it presupposes that there are exactly 4 corner pieces, and that, well, that's not untrue, but it will presuppose that the conditions by which we find a corner piece will only ever return 4, and that's not true. Because if you look at these pieces right here, when this piece is rotated, this middle piece is rotated, it could potentially look like a corner piece in that it has 2 sides where the values don't appear anywhere else on the board. It just so happens that when this is rotated, it has either 1 or 3 sides or 0 sides that appear elsewhere on the board. So it would be 1 or 3 and never exactly 2, which is what we found here. Because that's really all we were looking at here, is we were trying, this is like the shitty shortcut way, is saying, hey, for every state in this tile, if we rotate it, so which is looking at all the different states of the tile, for every rotation in the tile, is there a state where it shares exactly 2 sides with the board and not 4 sides? And we happen to get lucky. So I mean, like, we can move on from this, but I doubt this is going to help us in part 2. I feel like part 2 is going to require that we actually assemble the whole fucking board. And quite right, so it should. Like, I feel like that's fair. So I think we're about to get screwed here. And let's find out. Okay, now you're ready to check the image for sea monsters. And here it comes. The borders of each tile are not part of the actual image. The borders of each tile are not part of the actual image. Start by removing them. The borders of each tile are not part of the actual image. Well, shit, what does that mean? 1, 2, 3, 4, 5, 6, 7, 8. So we're just chopping them down, the tiles, and remove the gaps to form the actual. So here we go. This is, yeah, we needed to reconstruct the actual tiles. So yeah. So there's no way around it. Like, we do need to reconstruct the actual map, and that's the shortcut that we spent so long making in part 1, is like, oh, let's be clever and maybe we don't need to reconstruct the actual map. Well, you know what? These chickens have come home to roost. Now we need a map. So okay. When looking for this pattern, and we want to look for this pattern in the image, the spaces can be anything. Okay, so let's talk about, I mean, we're not starting from scratch, but I feel like we're kind of starting from scratch. We're gonna have to go back and fix part 1 before we move on to part 2. Okay, so when looking at this pattern image, the spaces can be anything, only the hashes need to match. Also, you might need to rotate or flip your image before it's oriented correctly to find the sea monsters. In the above image, after flipping and rotating it, there are 2 sea monsters marked with 0. So this is telling us a bunch of things. So it's telling us that we're going to need to flip and rotate the maps themselves. So we could either do that. We could either flip and rotate the maps themselves. Okay, you might need to rotate or flip your image before it's oriented correctly. In the above image, after flipping and rotating it, to the appropriate orientation, there are 2 sea monsters. So do the sea monsters always face the same direction? how rough the waters are in the sea monster's habitat by counting the number that are not part of a sea monster. I'm going to assume the sea monster always goes left to right like this. It's always in the same orientation. So if there's two, there's two. So this part 2 tells us a couple of things. It tells us that we're going to actually need to rotate the entire map, which means that instead of what we were doing before, which is getting the sides and rotating the sides around, we're actually just going to need to rotate the entire map. So each tile would have 4 variations, and each variation of the tile should include its complete map. And then we can just figure out the top right, bottom left based on that. So we took a wrong turn, like not a wrong turn, but we took in retrospect what was the wrong turn there. And because it didn't come in useful later on. So we're gonna want to flip the tiles. So we're gonna want a method basically that takes in a big thing like this and can flip it, and then we can use that to flip the tiles. So in retrospect, that would have been the right way to go about. Oh, David's here. Hey, David. 8 variants, 4 rotations, and flipped. Yeah. So that's yeah. So that's what I found. I think earlier, but I was just, so part 1 was just calculating the tiles themselves, like by, I don't know if you were here for part 1, probably not. But in part 1, yeah, I was like getting the top left, bottom right IDs basically, or fingerprints. And I was just calculating the sides, and then I was flipping them and parsenting those. And it turned out like every decision I made in part 1, it seems like ended up being like, oh, that's not going to be useful in part 2. You actually wanted to do the other thing. And it's just as well, because I didn't feel good about part 1. I didn't feel good about the answer and how I got the answer, because it just so happened that there were 4 corner pieces. I didn't bother reconstructing the entire map. Just jumped in, took exactly the same choices you did, for better or for worse, maybe. Yeah, basically what I did is I just found the corner pieces, the tiles that had to be corner pieces, and I multiplied their IDs, and I got lucky because the corner pieces there didn't have to be only 4 of them. There could have been 6 or 8 that qualified as a corner piece, or more, and it just so happened that there were only 4 that qualified as a corner piece. Anyway, so we are gonna have to reconstruct the actual tile map, because then we have to like trim the outer layer of each one and glue them together again to make a new tile map, and then we need to rotate the whole tile map. So I think this is what we're gonna have to do. And then in finding the sea monster, like this array, I mean, this can be effectively looked at like this. So what a sea monster becomes, this is sort of where I was going before we started chatting. A sea monster basically becomes this. So basically what we need to do is we need to find, for every one, we need to see if there's one at +2, and then one at +6 and 7, and one at plus whatever. There might be, what we could do is we could turn it back into a string, except these actually could be anything. I mean, this could be a whatever, and it still matches a sea monster, so we can't do a string match. We could maybe make like a weird regex, but it might be just as fast to say, hey, is there one at +2? And if so, is there one at +7 or whatever that is, and one at +8? And then if any of those fail, we just keep moving. But we don't even need to check all of them, because we only need to check between like that one and that one, because a sea monster is only so wide. But anyway, that's probably not the optimization that we'll care about. So let's fix part 1 and do it the proper way. 1.old. like coffee. So we're gonna keep this code around just for reference as we fix part 1 and do part 1 the correct way. All right, so part 1. So what's the right way to do part 1? The right way to do part 1 is we take in a tile, we have our tile, and then what we do is we flip it. And we want, each tile is going to have 4 variations of tile, and those variations of tile are just going to be tile flip. So we're going to flip, or I guess rotate. And rotate tile is going to give us a tile with the same ID, but different top, right, bottom, left. And instead of just the fingerprints, we're actually going to want, well, actually, so for, I'm getting ahead of myself. So let's rotate. Let's rotate something. Let's rotate our rows. So when you rotate rows, what is that like? So you got 1, 2, 3. Actually, let's not do this as, let's get rid of the array notation. 1, 2, 3, and then you got 4, 5, 6, and then you got 7, 8, 9. Oops. Okay, so when you rotate these, what do you get? You get 1, 2, 3. And then you get 4, 5, 6. And then you get 7, 8, 9, like that, right? So, okay, so your first row becomes your last column, and your last column becomes the reverse of your bottom row. So effectively, we're doing a similar thing to this, except this is, so this, what we're doing here is this is specific. So this is ugly. So let's think about this. Let's think about this as just a series of rows. When I'm going to read in this new row, what I want is so the first row is going to be the first column from right to back. And then I guess what we could do is for 6, 7, 8, and then 9, O, A, B. Oh God. Okay. It's just to help me think about it. And then what is this going to be? C, D, F. Okay. Okay. This way I won't get stuck into thinking about it through, like, the edges are all that matters, because it's not. Okay. So when we are making our new row, where do we I don't know why I kept that. So when we're making our new first row, what are we actually reading from? We're reading from the rightmost column backwards. So C, 9, 5, 1. And then when we go to our second row, we're reading from the second column backwards, which is D, O, 6, 2. Is that right? D, O, 6, 2. Okay, so that's not so bad. We can just do this throughout, and then E, A, 7, 3. So E, A, 7, 3, and then F, B, 8, 4. F, B, 8, 4. Yeah, and then that's the rotation. So we rebuild it row by row by doing that nth column reversed. Okay, so this is what we're after. So we can say rotate, and that's going to take in rows. So we already know what rows are. Okay, so we're going to need a return array, and we're going to say for each. I mean, really, just we want to know in 0 to rows length -1, 0 up into not including rows dot length. So for I index in, and then we're gonna do the same thing for. That's gonna be our, and then yeah, okay. Then we can just do minus by -1. So we're going to say that many times, and that's going to fill out our new rows. And then we're going to just say we're going to want to map rows by that index. Okay, and then we're going to want to reverse it. So new row equals, for snake case, it's more readable. New row equals rows map, and then we're gonna go row at index, and then we're gonna want to reverse that, and we can just ret push that, ret push. Okay, and then we're gonna return ret. In fact, we could just do whatever, this is fine. Okay, so rotate, and it's not rows, it's this dot rows. Okay, okay, so let's try rotating the first tile. So let's get rid of this crap over here, and let's say, okay, parse input, so tiles equals parse input tile, parse input input, and we'll say tiles, so tile equal tiles. Okay, and so let's log tile dot rows, the first row. Okay, let's just see what that looks like. Okay, and what if we just log tile rows and see what that looks like? Okay, and then we want to join. Let's join it with a new line. Okay, so that's what that looks like. And then let's do, so rotate is going to give us new rows. Rotate. Okay, and so let's tile rows, or rotate rows join, and then let's log just that in the middle, so we have a space. Cannot read property join of undefined. Oh, because that is the rotate, is the rows. Okay, well that's fucked up. Oh, right, because those, where was it? We need to join them because they're strings. So no, where are we? Up here. Rows map. Let's just say new row equals. Okay, and then we'll say new row dot reverse dot join. Join it with that guy. All right. So this should match that, and it 01001111. Oh, okay, so this looks correct. let's check the next one. 01, 01, 101, 010. Okay, yeah, so this looks like we're rotating it. Whoops, so rotate. So what do we want here? Do we want just the rows, or I guess what we want is we want so this is giving us tile text, which is giving us, so I mean we could reconstruct the entire picture and just parse it again. Or we could have a tile having 4 states. Or we could have rotate be destructive. We could have rotate be a destructive operation. You know what? I'm okay with that. Rows equals red. There you go. So now rotate is a destructive operation. So we can call down here. So we can log that, and then we can say tile dot rotate. And actually what we'll do is we'll make a destructive operation that returns itself. So rotate, and then rows join log that. So that should give us the same output. Of course, we should log nothing, just so we have a split. Yep, cool. Okay, so that still works. So now we've got this destructive rotate, which I miss Ruby because you can make a rotate bang to make people realize that, hey, yo, this absolutely will destroy this output. I think in CoffeeScript actually we can just say rows equals that, but I don't know. I don't know if you find that particularly more readable. Okay, so this will rotate, and then we don't need to worry about this rev equals false. We can just get the fingerprint of rows and fingerprint of rows. Don't need to worry about reversing it anymore. So we can just parse in, a string, place replace, 2 like that. So that can fingerprint us. Cool. So fingerprint rows, fingerprints, rows. Get rid of those. And we can get rid of these rev equals false things because we don't care about those anymore. Okay, so now we got top, right, bottom, left. So judging on the number of permutations, there's like, what is it? There's 10 things per tile. So how many combinations is that? Like, how likely are we going to have collisions? Because we could brute force this. Let's find out. Parse int. Here, let's get rid of all that stuff. We don't care about that. So this is the highest number that we can do. So let's log parse int that. So 1,000. So there's 1 in 1,000 chance of a collision, which means that if 2 pieces happen to match up, that's a 1 in 1,000 chance. So I feel like if we just randomly grab a tile and start sticking other tiles to it, if they match, the chances of that tile being in the right spot are pretty high. And so I feel like even though there's a high number of potential combinations, like the chances that we'll advance to the next tile being correct are probably pretty good. But what we want to do is we want to make sure that we start with a top left tile, because otherwise, I guess what we could do is we could also cache the next tile. like we could say, hey, for this number. So, I mean, we can really build on a lot of what we've done previously, which is like we can do the caching, or we could try to intelligently start with the first tile. I feel like maybe caching would be the easiest. So like, hey, I'm a tile, and what could possibly be connected to me? If we can cache the result of that, then it doesn't matter how inefficiently we start. We could start in the middle, and then as soon as we get to the middle again, the rest would just fill in because it would be cached. So we could, so the problem is that the tile is keyed by ID, but we also have rotation to consider. So unique side values we don't care about anymore. States we don't care about anymore. We're actually just gonna rotate it. And so we'd rotate, then next tile, then, I mean, that would only increase the number of things by 4 per join if we had it cached, which is better than, you know, like 100 or an average of 70. But maybe what we can do is we'll leave the tiles in the order that they were before. So we'd have to rotate them at most 4 times. So on an average of 2 times. But every time we try them, we're gonna have to, maybe what we'll need is we'll need to store the rotation of the tile. So we'll have to find so instead of modifying the tile, maybe what we'll want to do is we'll want to make a new tile, and we'll want to key it by the rotation of that tile. And so we can have 4 rotation values, and then that way when we say this tile joins to the next tile to the right, we will want to say that it joins to the next tile to the right. So tile 1 rotation 0 joins to the next tile on the right is tile 2 rotation 0, or tile 2 rotation 2, or something like that. So then that way we can cache that chain. Oh, David's saying things. I just grabbed an algorithm off the shelf. It's non-trivial. Okay, so it's a non-trivial algorithm to implement. So I mean that's David's way of warning me that this could take a long ass time. What time is it? It's 5. I mean, I started late today. I started at like 2:30 or something, or I don't know, close to that. Oh, for rotation. So I mean, I've got the rotation part working here, but this just rotates like a field of values. So that works. But what I'm worried about is like finding the permutation of the tiles. So I'm basically redoing part 1, and I want to actually make the tile map for part 1. So there's another part to this, which is that I need to know how many columns and how many rows there are. So I guess I can figure that out by the number of tiles. So it's the square root of the number of tiles. So if there's 9 tiles, it would be 3. Do I have it? So no, so what I'm actually doing is I'm rewriting part 1 to make the actual adjacency table. I don't have one right now. And that's what I'm doing. And then I'm going to make a mega tile out of those, and then I'll just rotate that 4 ways. That's my plan anyway. So part one, I cheated and I just found the corner pieces, the pieces that must be in a corner, because they had exactly two sides that didn't fit with anything else. And now I'm regretting having taken that shortcut, because now I actually have to do this. Okay, so you say it's a good plan. It's a good plan what I'm doing now, I hope. Okay, so I guess the question is, I've got these. So I've got these tiles, and I want to find out an efficient way of stringing them together such that I can find the next tile. So I guess what I want to do is I want to find out if the tile that I'm adding now will fit in the position where it should be. And I guess what I mean by that is I've got like a tile, 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 tile. So let's imagine I'm adding this tile, and I want to know if any of the four rotations of this tile has a left that matches the previous tile's right, and the previous row's this top matches the previous row's bottom. So that's sort of, I think, what I want to do. And then really this is the only value that I need to do. Then this can just go into there, and then I'll move on to the next one in the array. So, and what does this mean? It means that this -1, the right is the left, and then this minus row length, so would have the bottom equals the top. Why do you have to check multiple tiles? Why do I have to check multiple tiles? If you have a tile T and a tile S, they fit together or they don't. Yeah, but like up here, the bottom of this one matches the top of this one. And I don't think, I mean, it might be that it's so unlikely for them. So I mean, I could just find 3 that fit together and then try to find the ones that fit downwards and just hope that they line up. I mean, maybe that's what I should do. Maybe I should make a row, and then I should just try to grow them out in every direction. Or maybe what I should do is I should just keep trying to find pieces that fit. Yes, you don't have to check anything else for those 2 tiles. Oh, okay. So basically, I can be guaranteed that every edge is unique. Yeah, it's solvable. It's not general purpose. Yeah, okay. So I think David's advice is basically just try it the easy high assumption way, and it'll probably be fine. And I think he's probably right. So because there's 1,000 values, possible values for this number, and then 12 times 12, there's going to be 144 tiles, so that's 12 or 11 plus 11, so there's going to be 22 joins. Is that right? Or 11? No, not 22. It's going to be 11. It's going to be 220 joins. Anyway, I don't know. The chances are in my favor that would work out. So we could try that. We don't need to make the most robust thing on the planet, I guess. And in this case, it'll be 3 through 3, 3 through 3. So it'll be 12. There's 12 joins for 9 tiles. And then there'd be 222 joins for 144 tiles. Is that right? No. Yeah. So we're still way under the 1,000 limit. They're likely to be unique, and if they're not, we can deal with that. So let's I guess what we'll do is we'll just try to find a row, and then we'll try to add a row to the top and or to the bottom of that row. In fact, what we could do is we could just make rows. Yeah, and then once we have that map, then we're fine. Okay, so let's try it. Let's try finding a row. So I guess to find a row, what we need to do is we need to make a tile, and then we need to do that thing from earlier, which is, we'll try to find, I mean, we could just try to find the left, top, bottom, and right match for that tile. And we could grow it like a crystal. We could just bleh. But no, that's gonna be annoying. No. The problem there though is that if we have a tile and we rotate it, then the bottom piece is going to connect to the rotated previous right. So we've got, we can find our corner pieces. We can find our corner pieces. Okay, so possible corner state. We actually don't need this anymore. We don't need this corner pieces. We don't need all side values. We will need multi-array eventually because we need to multiply them together. Okay, so we've got a class tile. I can rotate it. Excuse me. And you know what? Let's make this parse. And then the constructor will just take in the ID and rows. And the reason I'm doing that is because that way we can easily generate new tiles with the same ID. So, okay, we're gonna parse that, and then at the end we're gonna say new tile with ID. I guess this can just be ID and rows. ID, rows, ID, rows. And then down here, what we can do is instead of assigning this, what we can do is, this is our new rows and we still have ID. What we can say is we can new tile with ID and rows. So let's see if that works. So this is going to be, parse input is going to be tile.parse. Cool if I could just map it through that. I wonder if I can do that, parse input. Let's find out. Let's log parse input that. And no, this is not a constructor. Okay. So it's going to text and then tile parse text. Okay, so this gives us tiles. Cool. And okay. And then a tile has 4 variants, and that is going to be, so maybe what we should do is we should actually have constructor ID, rows, and this can be rotation, or how about version? No, orientation. We'll just call it R0. Cool. And then rotate, so we can do that, and then R plus 1. Cool. And then what we can do is we can say we can actually just pre-calculate all the rotations. So we could say, well, oh, but we also need to flip it. Goddamn. Okay, so we all right. Flip. Okay, so by -1. So for index in rows length by -1, we'll say new row equals new row equals rows. We'll just we'll do one of those flips. Oops, come back. Where'd you go? There you go. Rows equals rows length minus index. And red push that. Okay, and then that can be, so we're gonna have rotation and a flip. Okay, so this is where caching comes in. So all tiles equals that, and we'll say so we'll say all tiles ID and rotation. So this is going to give us rotation all O. So we want to actually just join these together. What we can do is we can join them by, so that's going to give us rotation, and also we want rotation flip. We want every combination of rotation and flip. So rotation and flip, but rotation for flip is the same as rotation, so it'd be rotation mod 2 flip. Okay, join or equals to that. I guess, well, we're pretty guaranteed that when we do parse, it's going to do this, but whatever. So that's parse, rotation, and flip. And flip is going to be equal 0 or 1. Okay, so so we can say all tiles, and we're going to rotate or equals R. Oh, this is going to be flip. This is flip that we're talking about. Okay, rotate. So we're going to say, okay, so all tiles. So rotate equals the current rotation. And so we're going to say plus for mod 4. So plus 1 mod 4. So that's going to be new R. Because this is going to flip it like that. Rotate. Oh no, it's not. Let's get rid of this mod 2. Okay, all tiles. And then the flip is going to be equal to whatever the current flip is. Okay. And then tile equals, so now we can return tile if all tile. Okay, so we're going to do that. Otherwise, we're going to say all tiles equals that. And of course, we also need ID. Where is ID? This ID. And ID. So in flip, this can just be flip. And we'll say flip. Maybe I'm overthinking it. Probably overthinking it. Okay, so generate. You know what we could do is we could actually just make a class method rotate. Rotate, and this takes in a tile, and it does this. So so it would take in a tile with a rotate and a flip value, and what it would do is it would do all this for me. Cool. So okay, so instead of at rows, it would be tile rows. And then, okay, and then what it could do is it could get the ID. So it could get, right, oops, could get ID rows, rotation, flip equals tile. I wonder if that works. Let's find out. And then this could be rows length. This could be rows map. Right, push whatever. Okay, and then what we want to do is we want to make sure that the new rotate is mod 4, and then because it's flip, it's just flip. And then what we would do is we would, okay, oops, and then return tile if all tiles, and then we have ID rotate flip. And what we could do is we could generate, we could make a rotate function here that does all this stuff. Rotate tile, rotate. How about just rotate? And then rows. This just takes in rows. And new row and ret push, and then spits out ret. Okay, and then so we can actually just say or equals rotate. But this would be rows. Nope, I'm in the wrong place. Rotate. So we would say tiles or equals to, and what is or equals to new, or it would be tile dot. Yeah, new tile, and that would take ID, rotate rows, and then it would take R and F. So ID, R, F. Okay, and then we gotta close that. Cool. So that's rotate, and then flip would be similar, where we say we can get rid of this rotate and flip, except in here we're updating the flip. So flip equals flip plus 1 mod 2, because there's only 2 values for that, and then we do, except we need to do flip rows. So actually let's get flip back, because I had that in here. Okay, and this would be flip, oops, up here, flip rows. It's like a British person saying Philip. Flip ret equals. Okay, so in rows.length, rows push rows length minus index. Cool, and then we'll go ret. So that rotates rows, that flips rows. These will come in handy next time, which is why I bothered extracting them. So all tiles we're gonna want to. We're actually this is kind of shitty. So I mean, we're gonna have to reset all tiles between things. So that's annoying. Anyway, all tiles. This is our like identity map, and it's kind of like it's baked in, which is this is really shitty. But you know what? Let's make it work. Let's make it work, butch. All right, top right, bottom left, cool. So let's see what we got. Okay. Oh, parse input. We could do it in here in parse input, and that could give us back all tiles. So what we could do is we could say we could do this in the constructor. Was we could construct all tiles and then no. Okay, so we'll say all tiles equals that, and then we'll return. I guess that's another thing we could do is we could just attach. we could attach all tiles, the array, to each tile itself and make like a circular structure. All tiles, okay, and then we could say tiles equals. So it's gonna give us like I feel like maybe what we could do is whatever. I'm overthinking this, and we can overthink it later. This is going to parse the tiles. Okay, so we got rotate, and this one is flip. Okay, so let's just test this. So tiles equals parse input, and then let's log tiles first. Let's just see what tiles first is. Okay, and let's log tiles first flip. Oh, there we go. Tiles first flip is not a function. Right, because we don't have any convenience methods here. So flip is gonna be at so it's gonna be tile flip itself. Okay, and then rotate is gonna be the same. Rotate. Okay, tile, except it gives you blank rows. ID index in 0 to rows length by -1. So this is gonna flip it vertical, or flip around the horizontal axis. Is that how you say? No, flip horizontal is this way and flip vertical is that. I'm gonna just update flip to be flip V. Just so, and rotate, I guess we can assume rotate counterclockwise, or clockwise rather. Okay, so flip vertical rows, so you get red. In fact, this is just rows reverse, isn't it? Reverse. Okay, what I'm doing. All right, so flip. Tiles flip is not a function. Tile, oh, flip V. Yeah, because I made it flip V. Okay, so what is this? Tile flip is not a function. Oh, yeah, right. Tile flip B. Flip B. Okay, so nan. Ooh, that's not good. Okay, so flip. It was flip +1, and R is R +1. Okay, let's try that. So this gives us flipped. So let's log tiles, and then we'll log tiles flip B. Okay, so we got tiles. So 0011, and then this is so flip vertical. Where's 0011? Oh, I guess flip is just rotate twice. No, it's not. It's absolutely not rotate twice. Okay. So 2311. Okay. So this is the top row, which would become the bottom row. 0, 0, 1, 1, 0, 1, 0, 0, 1, 0. Okay. Beautiful. A name only a mother could love. All right, so flip view works. Let's try rotate. Okay, so that gives it a rotate of 1. Let's try rotate. Rotate of 3, rotate of 4 should be rotate of 0 again. Okay, and it should have found that in all tiles. So all tiles. So let's reset the cache. Okay, so all tiles is that, and let's say log tiles dot values dot length. I guess it's object values. Values. Okay. Cannot read property 231100 of undefined. Why is that? 221. 221. What am I doing? Object values. 246. That's parse inputs. Cannot read property of undefined. Oh, maybe I do need to initialize it up here. That's not great. All tiles. Oh, it's because I wasn't doing it before parse input. So you know what? Parse input should reset all tiles for me. Parse input. Okay. And as long as I've defined it out here, then it's okay. Ugh, it's so shitty. Oh, I hate this. Okay, so okay, cool. So after we parse the first tile, log num tiles. So after we initialize the tiles, we got 9 because that's how many tiles there were, and then after we rotate it a bunch of times, we should have 12. And we do. We have 9 and we have 12. So our caching is working correctly, because otherwise this would have been 13. If we rotate it 3 more times, we should still have 12. Okay, cool. Okay, so we got rotate, we got flip vertical. Okay, we got tiles. Okay, so for tile and tiles. And so what are we going to have to do? We're going to have to generate some tiles, and we'll probably want to cache the next key of a tile. So we want a tile to be able to take in a set of tiles. Okay, rotate would be top, right, bottom, left. Let's just put these in line like this to get them out of the way. I think there's probably like a text editor thing I can do for these, but okay, so these are convenience methods. These are our fingerprints. And okay, so we got, oh yeah, there's these little arrows here. Okay, maybe I should just use those. Tile, tile, okay, and then we'll, hey, where's my arrows? Oh, it doesn't give me arrows. Okay, well, going back to this way. Okay, rotate, flip vertical, top right, bottom left, and there you go. We got our class methods. We got our constructor, which does nothing right now. In fact, our constructor doesn't need to do anything ever. Just needs to provide default values and assign things. which you can do thanks to those handy dandy this arguments. Okay, so next tile, what we want to do is we want to find a fit for the tile. So we want to be able to provide a direction. And we want to, so we, what do we want to do? I guess what we want to do is we want to find a tile that fits two tiles. So fits, and the fits is gonna matter. So top left, bottom, or top right, bottom left. And realistically, we're only going to be asking it to fit where its top or its left fits something. So top, null, and left. Like that, right? So we want top and left. So we want this top to equal this value. We want this left to equal that value. And that would come from either the top tile or the left tile, or both. And so each one of these is a constraint. So if top, we'll start with the top, and we'll say, so this is if this tile fits this top and this null. So if top is top, and so if top and top is top. So I guess we can just say if top is in null and top, and oops, left. Okay, so this is going to give us these fingerprints. And you know, like we could also fingerprints. This could be an object, and then this could be FP's top. You can just cache them. Okay, and we'll do the same thing with these three as well. That way we don't need to recalculate them all the time. Let's match these up. There we go. And then we can have at fingerprints. Okay. Oops. There you go. Cool. That'll cache them. And now what are we doing? Okay, and then top right, bottom left. So this is probably one of those cases where it's just like premature caching. don't worry about it. The lesson is always do it. So if it fits top and left, so those are the two potential things that we care about, or maybe both. So what we want to do is we want to create like a grid, and we want to make sure that every tile fits. And I guess what we could do is we could rotate the tile 4 times for rotation in I guess, or for rotation ID equals 1 or 0, not including 4, in. If that, then we'll return tile if, so we'll say tile equals rotate is rotate. And I guess we've already got the initial rotation. Okay, and then if that fits for tile and tiles, so we're going to rotate, and if it fits, then we'll put it in. I guess we can just rotate it 4 times. Tile dot rotate. Rotating is pretty cheap. Okay. And then else will return false. So we're going to return the tile in its and flip. Flip ID in up to and including 1. So this should be up to and including 3. Here, let's double check this. I always confuse these. JavaScript, try JavaScript, and we'll just say rows equals and alert rows. So is that up to and including 3? Then let's find out. 1, 2, 3. Yeah, perfect. And then up to and including 1. Okay. So return. So we're gonna say, yeah, tile. Oh yeah, this isn't right. Let's do the flip out here, and then the rotate in here, and then this was tile rotate, tile dot rotate, and then up here we're gonna tile flip, tile equals tile flip. I guess here should be tile equals tile rotate, and we can return tile if top in tile top. This isn't great. This is sort of like, this logic should probably be outside of this tile. All we care about is this here, top in top, and then we can do this somewhere else. Oops, we can do that somewhere else. I guess what we can do is we can have every permutation of tile. So what we could do is we could say permutations, and that would just say for, yeah, all of this stuff. Oops. Hi, why are you like this? There we go. Oh God, There we go. There we go. Okay. So for flip ID and for that, so we could say red equals, and we could say red dot push tile flip. So that'll flip it twice, and for each flip it will rotate 4 times. Tile equals tile flip, and then red push. I mean, we could just do this on a separate line just to make it a bit more readable. Tile, tile, and tile equals tile rotate. And we'll say tile 4 equals to self. So this will give us all permutations, and oops, and then we want to return red. So this will give us all permutations, including this one. Let's check that. So tiles dot permutations. It's a permutations. Yeah. Okay, and let's log that. So this should give us tile or equals. Why is this angry? Variable tile can't be assigned with because it has not been declared before. Oh, okay. Tile equals this. I mean, it's always gonna. There you go. So it says tile flip is not a function. Oh, because it's not flip, it's flip v. Flip v. There you go. Get rid of these. So this is going to give us, right, a bunch of tiles, and we will length, just test length of that. It gives us 10. That's not correct. Oh, because it's 0 to including 3. Unless tile. Oh, you know what? This is a. We don't want to do that. We want to just push tile in here. Okay, and that gives us 8. So that's 8 permutations. So, okay. Tile equals tile rotate, and then red push tile. Cool. So this starts us off with 1 tile, and then it flips it, rotates it, rotates it, rotates it, rotates it, flips it, rotates it, and we do that, and we get the resulting number, so which is 8. So that's how many we want. Perfect. Cool. Time is at 5:45. Ooh, crap. It's getting late. Maybe I should take a break. Gotta take the dog for a walk. Okay. All right, I'll finish up this bit, and we'll take a break, and then we'll come back to it. So we got permutations. So we got a tile. Let's just take a quick look at what it is that we want to do. Okay, let's red equals that, and tile equals that. We'll just get these out of the way. Okay. Cool. Okay, so what is it that we're going to do now? So we've got a tile, we've got a flip, we've got a rotate, we've got an identity map. We can get all the permutation, all 8 permutations of this tile, and we've got a way to determine if this, for any tile, we've got a way to determine that its left should have that right value, and that its top should have that. So I guess what we want to do is maybe we want to make it more general purpose. We want to say, hey, does this tile's left, can it be that tile in its current state? And if so, can that tile be that tile in its current state? So I guess, I mean, the values are fine. We're just basically saying, hey, is the top value this or is the top value that? And what we can do is we can cycle through all the permutations of that tile until we find a match. And then we'll cycle through all the available remaining tiles until we have a match. So the goal is that we're going to start with a tile, and we're going to go through and we're going to try and build up an entire map. And what we should do is when we find a tile, find this tile that does match this position, what we should do is we should mark it and we should cache it somehow so that the next, I guess what we can do is we can just say next tile all the time, and we can make sure that the next tile, which would wrap around and around, the left should be equal. So maybe like this fits thing is overkill. The left should be equal, and if there's a tile 1, 2, 3 previous, that its bottom should equal its top, and we can do that maybe as a stretch goal. So we just want to find the next tile, and we find the next tile's rotation, and then so really we want to find a tile with no previous tile. We want to find, and there's going to be a lot of those because there's going to be a tile, but there's going to be a tile where no permutation has a previous tile maybe. And I mean, that's also an assumption, but it's probably a good assumption. So that's okay. That's what we're going to do. I'm going to take a break, and then when we come back, maybe in like an hour or two, what we're going to do is we're going to try and find. So we're going to do one of two things. We're either going to try and find the first tile, the tile with no previous tile, in any permutation. And then what we're going to do is, we're going to cache the next tile. Or we're going to find all possible next tiles. Yeah. Anyway, I'll think about that when I'm out. But for now, I am tired and hungry. My dog is also presumably raring to go out, so I'm going to take a break. And we'll see you again in a couple of hours, probably. I'll post on Twitter and on Toronto.js. So